Hi guys, Dr. Burns here. We are looking at section 1.2 where we're going to start getting into the solutions to a differential equation and what that would look like when we actually solve a differential equation. Please make sure that your cell phones are put away and turned off. Cell phones are such a distraction to your concentration, and I want to make sure I have your complete attention for the next 10 minutes or so. So let's start with section 1.2. Make sure you have your notes out and you're taking notes in your course packet as you follow along. As I mentioned previously, we're going to learn various techniques this semester for solving differential equations, but I want to just start off with what we mean by solving an equation. What does that look like? So an explicit solution is any solution that is given in the form y equals, and this funny notation is what our textbook uses. They call this, I think this is the Greek letter phi or phi, whichever way you say it, phi of x. But basically it's a function of x. So y equals some function of x. That's the format I'm looking for when I solve a differential equation. If that solution is y equals blah, blah, blah of x, that's what we call an explicit solution. Just like when we write a function, if I say y equals x squared, that's a function that's explicitly written as a function of y in terms of x. Implicit is any solution that's not written in that form. So in other words, remember back in Calc 1 we had implicit differentiation, and that was where we worked with an equation where the y was part of the function itself, right? Or wasn't necessarily a function, but the equation, where y was embedded inside the function. So the implicit solution is written in that same type of format where we don't have y by itself. That's the only difference. You don't have to worry too much about the difference in terminology. Just know that both solutions could show up. Let's look at a couple of examples here. Number 1 says, show that y equals x squared minus x to the negative first power is an explicit solution to the given differential equation. So let's talk about a couple of things. This is a second order differential equation because we've got a second derivative in the equation. So to show that something is a solution, I think the best way to do that is to go ahead and take what they're giving you as a solution, and you're going to substitute that in for the equation wherever the y or any of its derivatives show up. So in other words, in place of this y, I'm going to put the original function. But I also need to know what the second derivative is. So I'm going to find the second derivative here. So if y is equal to this expression, we know that the first derivative, dy dx, is equal to 2x minus, bring the negative 1 down, so plus x to the negative second. And then the second derivative, I'm going to go ahead and find that only because that's part of the equation, is going to be equal to 2 minus 2x to the negative third. So I'm going to go ahead and substitute those into my differential equation. The second derivative was 2 minus 2x to the negative third minus 2 over x squared times y. Now remember, y was the original expression they gave me up here. So that was x squared minus x to the negative first. And if this is in fact a solution, then this should simplify to just 0. Now notice I didn't actually need the dy dx, and that's because there was no dy dx in the equation, in the differential equation. I only used the dy dx to get to the second derivative because I did need that. So let's clean this up a little bit. I'm going to drop these parentheses here, and I'm going to distribute this negative 2 over x squared. So I'm going to have minus 2. Notice that x squared is going to cancel. And then I've got plus 2x to the negative third. And hey, guess what? That does, in fact, equal 0. So I am good to go. Let's do the next one. Show that this expression is an implicit solution. Again, just terminology, implicit because of the way it's written, to this differential equation. Now, before we get too involved here, I need to find dy dx. So remember how we found the derivative using implicit differentiation back in Calc 1. Let's review that really quickly here. So to find the derivative of this equation, I'm going to just go down the line and take the derivative of each term with respect to x. Start with x, the derivative of that is 1, plus the derivative of y, which is dy dx. And you could also write y prime, it doesn't matter to me. Plus, now to take the derivative of e to the xy, I have to use a chain rule, so that would be the derivative of the outer evaluated at the inner times the derivative of the inner, which requires product rule. So we have 1 times y, so derivative of 1, or derivative of x rather, times the second recopied, plus the derivative of the second times the first recopied, and then equals 0. This is a bit messy. We can solve for dy dx if the algebra is not too bad. That's an option. Let's go ahead and do that. I don't think this one is too terrible. I'm going to distribute the e terms. So we have 1 plus dy dx plus y e to the xy plus, let's see, x e to the xy dy dx equals 0. And then remember, to solve for dy dx, you want to get all those dy dx terms to one side. So let's do a little bit of algebra here and see if we can get that. So we're going to have dy dx, let's see, plus x e to the xy dy dx equals -1 minus y e to the xy, and then factor out a dy dx, x e to the xy equals -1 minus y e to the xy, and then finally you have dy dx equals -1 minus y e to the xy over 1 plus x e to the xy. So I'm going to substitute that expression back in for dy dx into the original equation that they gave us. So we have 1 plus x e to the xy times -1 minus y e to the xy over 1 plus x e to the xy plus 1 plus y e to the xy. And the question is, does that equal 0? And you'll see here that it does. These terms, of course, divide out. So you're left with -1 minus y e to the xy plus 1 plus y e to the xy, which is, of course, 0. So we are good to go. You may have noticed as well that back here, let me highlight it, in this step, you had dy dx times 1 plus x e to the xy. That was actually this expression right here. If you had noticed that, you could have just substituted in this side of that equation, and that might have been a little bit shorter way of getting you to the same result. You still would have ended up with 0. Or you could just solve it for dy dx the way we did. Either way you do it is fine, no problem. Let's do one more here. Show that y equals sine x minus cosine x is a solution to the initial value problem. With an initial value problem, they are giving you an extra piece of information about the solution, and that would be an ordered pair. So they're telling you this is your differential equation, and they're also telling you that y of 0 equals -1. That means the specific solution curve they want goes through the point 0, -1. That's from this piece of information. They're also telling you that dy dx, the derivative at x equals 0, has a slope of 1. We'll come back to that part in just a moment. Let's start by just verifying the original differential equation solution without worrying about the initial condition. So I'm going to start by finding the first derivative. So dy dx would be cosine x plus, let's see, no, I'm sorry, wait a minute, derivative of cosine, oh, I'm sorry, oh, I had that right, I'm mixing up my negative signs. So that would be plus sine x, right, because the derivative of cosine is negative sine. So the second derivative then would be negative sine x and then plus cosine x. So if we substitute that into the differential equation, we have negative sine x plus cosine x plus the y expression, which was sine x minus cosine x, and that of course does simplify to 0. So we're good to go there. Now let's talk about the y of 0 equals -1. So if we substitute that information into the solution equation, we should have -1 equals sine of 0 minus cosine of 0. And that does, in fact, work. So we're good to go there. Let's go ahead and just verify the derivative expression as well. 1 is equal to, so I'm using this equation now, 1 is equal to cosine of 0 plus sine of 0, which of course is just 1. So we are good to go there. So that's how you would verify it if they give you an initial condition. Last little bit of information I want to just mention is something called the existence theorem, and there's a little bit more to it than this, but this is basically the gist of it. It says it guarantees that under certain conditions, the initial value problem, so like we had in the previous example, where they give us an initial condition or an ordered pair they want the solution to contain, will in fact have a unique solution. And we'll see that off and on throughout the course when we look at an initial value problem, that there's just one solution. All right, I think that's it. We will do some practice with this and talk about what we're doing tomorrow in class.